important concepts. So some of you may be aware, or maybe many of you would be aware. Are you aware how polyester is made? All the things that we wear, shirts and dresses, all those things, they are made from polyester nowadays. How is polyester made?
Condensation.
Condensation polymerization. Okay. Condensation polymerization of what? Other people
Of
can also respond. It is not only
Dimethyl
CR's
terephthalate
responsibility to.
and ethylene glycol.
Yeah, okay. Dimethyl terephthalate. So transesterification. But more commonly, Bombay Dyeing used to make it using dimethyl terephthalate. That's more costly. That's why they went out of business. Now, all over the world, it is made from terephthalic acid. So terephthalic acid, if you know, it is a condensation polymerization from terephthalic acid and ethylene glycol. So how do you think terephthalic acid is made? Organic chemistry you must have done.
Oxidation of 2,2 two methyl groups on the benzene.
What name would you give this?
One.
Oxidation of oleum.
Oleum. What name would you give this compound on the left hand side?
Xylene.
Paraxylene.
Right, paraxylene. Right. So it is made by oxidation of paraxylene to terephthalic acid. It is a high temperature process, about 200 degrees centigrade, 20 bar pressure. Right. Catalyst is there. There is a solvent. Catalyst is cobalt and manganese acetate, and there is a solvent which is acetic acid. So this paraxylene oxidation to terephthalic acid is our desired reaction. Okay, but unfortunately, because of high temperature, because of high pressure, because of catalyst, oxygen is there. Some amount of paraxylene also gets combusted. Right, you are supplying oxygen, you are having a hydrocarbon. Some of it goes to combustion, goes to carbon dioxide and water as well. This is our undesired reaction. Sometimes combustion may be desired. So for example, when we talked about last time, we talked about this methane getting combusted, right? So our combustion is a desired reaction here because we want to burn so that we can generate energy for whatever purpose, generating electricity and so on. But in this particular problem, paraxylene, we are not using it as a fuel. Paraxylene, we want to use it for making terephthalic acid. Therefore, our first reaction is our desired reaction. Second reaction, which is a combustion or burning of paraxylene to carbon dioxide and water, is an undesired reaction. Okay, so let me describe the problem. So here is the problem. So there is a reactor. There is a reactor. This reactor is at high temperature and pressure. This reactor, we are supplying paraxylene. So let me write it as Px for paraxylene. We supply paraxylene at the rate of 20 tons per hour. 20 tons per hour means 20,000 kgs per hour, metric tons. We also supply acetic acid, which is the solvent, along with catalyst and whatever it is there. So these are the two things that we supply. Paraxylene. So paraxylene is in the liquid phase. Acetic acid is in the liquid state. Acetic acid we supply at the rate of 80 tons per hour. Now we require oxygen. So we are supplying air for doing the oxidation of paraxylene. So let us assume that air contains nitrogen and oxygen only, 79 mole percent, 21 mole percent. Just let's simplify. Okay, air that is supplied. So imagine that this paraxylene is supplied at 100 degrees centigrade, acetic acid is supplied at 100 degrees centigrade, air is supplied at 200 degrees centigrade, 20 bar pressure. This also is 100 degrees centigrade, 20 bar pressure. Paraxylene is also 100 degrees centigrade, 20 bar pressure. Air that is supplied is let's say 100,000 nm cube per hour. So it is a continuous reactor in the sense that the reactor is continuous, operating at steady state, in the sense that when we say continuous, what we mean is that paraxylene comes in all the time, acetic acid comes in all the time, air is supplied all the time, products go out all the time, and the reactor operates at steady state. What we mean by steady state is if you measure the quantity or composition at any location with respect to time, then it does not change with time. That's what we mean by steady state. Some of you had asked this doubt in to me, so so this is the answer to that. Okay, so what will go out? So this is in the liquid state. Acetic acid is in the liquid form, paraxylene is in the liquid form, air is in the gas form. Liquid products go out and gaseous products go out. What do you think will be there in this particular stream, the liquid stream? What do you think will be there in this liquid stream?
Terephthalic acid.
Terephthalic acid.
Right.
Terephthalic acid.
Okay, so let's call this as TA for short. So terephthalic acid will be there. What else will be there?
Water.
Water will be there. Excellent. What else will be there?
So water would be in the liquid. I guess it would be gaseous.
All right, let us see whether water is in the liquid state or gaseous state. Right now, let me write it here only. Okay, what else will be there?
Acetic acid.
Depends which is
Correct,
the more
correct.
excess.
Acetic acid. So let us write acetic acid as ACOH, just to make our life simple. Whatever solvent is there, acetic acid will be there, right? Solvent will be there. Okay. If I say now conversion of paraxylene in the reactor is, let's say, 98%. What would that mean?
98% of all paraxylene would be.
Correct. 98% of whatever paraxylene is coming in is going to react. So will there be unreacted paraxylene?
Yes, sir.
Yes,
Yes,
sir.
sir.
So that unreacted paraxylene also will go out. Okay. What will go in the gas stream?
So water vapors.
CO2.
Okay. CO2 that is generated is a gas, so that will go away. What else will be there? Maybe water is there.
Some amount water.
Yeah, some amount
Oxygen
of
is
water.
in excess.
Oxygen.
Sir, oxygen.
If
Oxygen and
is in-
nitrogen.
yeah, if oxygen is in excess, then oxygen will also go. If it is in excess, I don't know. And nitrogen anyway is going to remain unreacted. Nitrogen is not reacting. So nitrogen will also be there. Let's right now assume that all the water goes in the vapor state. So that's not exactly correct. In reality, there is some amount of water going in this liquid stream as well. But right now, let us neglect that. Okay. The reasons are different, but let's not worry about that. Now, out of this conversion of 98%, if you have to do material balance and find out how much terephthalic acid is generated, I also have to tell you how much of the desired reaction occurs and how much of the undesired reaction occurs. Do you agree?
Yes, sir.
Yes, sir.
So this conversion means recall what our conversion means. Percent conversion. In fact, that's our next. That is what I wanted to talk about. So our percent conversion is amount reacted divided by amount fed into 100. Fed or supplied. Fed in the sense supplied. I'm supplying to the reactor or I'm feeding to the reactor. Now amount reacted is partly in the desired reaction and partly in the undesired reaction as well, right? So I have to tell you how much is in the desired reaction and how much is in the undesired reaction. So that number is called as selectivity. There are different ways in which people define selectivity. So somebody tells you selectivity, be careful how they are defining. The way we are going to define for consistency in all our lectures and exams and quizzes and so on is amount reacted in the desired reaction divided by the total amount reacted. So total amount reacted means what? Total amount reacted means what? It is amount reacted in desired reaction plus amount reacted in undesired reaction. That is the total amount that has reacted. This into 100 is going to tell us our percent selectivity. So conversion is amount reacted divided by amount supplied. So let me write that again here. Amount reacted in desired plus undesired reaction, both divided by amount supplied. That is our percent conversion. Okay, into 100 of course, and percent selectivity. So, okay, that's our amount reacted in the desired reaction divided by all the amount that reacts. All the amount that reacts means amount reacted in desired as well as undesired reaction into 100. So that's our percent selectivity. Okay, so now percent selectivity here for this particular case is, let's say, 99%. Okay, that means 99% of the paraxylene reacting is reacting via the desired reaction. 1% of the paraxylene reacting is reacting via the undesired reaction. Okay. Okay. Now acetic acid is there. Do you think acetic acid, it is at high temperature, so much oxygen is there?
It would also react.
Some amount of acetic acid also will burn. So other side reaction, acetic acid plus oxygen will go to carbon dioxide and water. Okay. How much acetic acid reacts also I will have to tell you now, so that you can do material balance. So how much acetic acid burns or reacts, whatever you want to call it. 40 kgs of acetic acid burn per metric ton. MT means metric ton. Metric ton means 1000 kgs of terephthalic acid produced. Okay. One more thing, we are going to write about the states. So when we write reactions, we also need to write what states these substances are. So as paraxylene in this particular case is in the liquid state, oxygen is in the gas state, terephthalic acid is in the liquid state, water we are saying goes in the gas state. Paraxylene in the liquid state, oxygen in the gas state, carbon dioxide is in the gas state, water is in the gas state for this particular problem. Okay. Acetic acid in the liquid state, oxygen in the gas state, carbon dioxide in the gas state, and water also in the gas state, right? So we also need to write what state they are in. Right now for material balance it doesn't matter, but it will start mattering when we start doing energy balances. Okay, is the problem definition okay with everybody? Is the description okay with everybody? Anybody has any doubts?
So what temperature are all the products coming out at?
So we don't have to do energy balance just now. So let's imagine that this is also at 200 degrees centigrade 20 bar. This is also 200 degrees centigrade 20 bar.
Sir, the pressure is absolute, right? Absolute.
Yeah, absolute gauge, whatever way you want to call. Doesn't matter really. But yes, if you want, you can take 20 bar absolute pressure just for simplicity. Reactor also is at 200 degrees centigrade and 20 bar absolute pressure.
And so the rate of the gas going in is Newton meter cube per hour.
Recall from the previous lecture, this N is not Newton. When we are talking about the gas volume, it means so many meter cube per hour referred to at STP. Recall our
Understood, sir.
this problem. Where did that go? Recall this problem. Pipeline problem, where we added carbon dioxide gas to measure the volumetric flow rate or molar flow rate of the methane going in. That time we defined N standing for the measurement of meter cube is at standard temperature 0 degrees centigrade and 1 atmosphere absolute pressure. So this 100,000 is at STP conditions. So this is the same as 100,000 meter cube per hour. Meter cube at what condition? Meter cube at STP. All right. Yes, everybody is okay with the description so far? Anybody has doubts about the description? So here is what we need to find. Quantities and compositions of all streams, right? This is what we need to find out. Just for simplicity, just for you to tell me the answer so that I can verify whether your answer is right or wrong. Second thing that you can tell me is composition of this flue gas. So we are going to call this as flue gas or off gas. On dry basis in volume percent, right? Remember, that's one more thing that we defined, important thing that we talked about. Percent selectivity, that is the next thing. We talked about Nm cube, N referring to meter cube at STP when we talk about gases. And then last thing that we talked about last time was dry basis without the water and wet basis. Okay, so do this problem. If you have doubt, just ask. Follow all these important steps. You will get the answer in no time. If you
Sir,
want
we have to find mole composition, right? Or weight composition.
of what? This,
Sir,
when
the
I say this
stream,
composition,
the quantities and compositions
so
in
if it's a liquid
terms.
stream or a solid stream, that composition we will usually write in terms of weight percent. And if it is a gaseous stream, we will write the compositions usually on a dry basis in volume percent.
Okay, sir. Thank you.
Right? It is a standard practice. But yes, good that you asked. If you want, you can write down all these steps on a big drawing sheet. You all have drawing sheets from last semester. Back of one of those drawing sheets, you can write down all these things, all these steps, and stick it on the wall so that it is always in front of your eyes. If you have any doubts, you can always ask. If you are stuck somewhere, you can ask.
So in both cases, we are assuming that complete combustion is taking place, right?
Complete combustion in the sense all the things is not reacting. Complete
Oh,
in the sense of no carbon monoxide.
yeah.
Yeah,
No
yeah,
carbon monoxide.
correct. Yeah, in the reactions, I have only written carbon dioxide. I have not written any carbon monoxide. That will happen automatically if air is in excess. I don't know, but whether air is in excess or not. But still, we are assuming that carbon dioxide is formed. No carbon monoxide is formed either by paraxylene oxidation, burning, or acetic acid burning. Whatever burns goes in carbon dioxide. Third very important thing we can find out, kgs of carbon dioxide is generated per metric ton of terephthalic acid produced. We'll talk about why this is important. Find means somebody will find from one of your classmates also.
Sir, can you show the side reaction of the acetic acid? Side
Huh,
reaction once.
huh.
The side reaction.
You want to see or what? What do you want? What are you asking, Praveen?
Sir, sir, the statement actually, the 40 kg statement.
Are you able to see now?
Yes, sir.
Yeah.
Thank you.
Yeah. Problem is kind of long, so that it's difficult to fit in one screen. If you are stuck somewhere, please ask.
Sir, can I tell the answer of the liquid stream only first, or
No,
calculate all?
calculate everything. Tell me this third one. If your third one and second one, if you tell me, automatically the first one will be correct.
Wait, sir.
Any answer, Keshav?
No, sir, I'm solving.
Okay. If anybody wants to have a break, they can have a break also for 5 minutes. We are not going to stop. Karthik, any answer?
No, sir, I'm solving.
Okay. Amol, any answer? Ankush, any answer?
No, sir. It's just
Are you stuck somewhere? You need a hint?
No, sir, let me try.
Okay, okay. Ansh,
Sir, I am on the last few steps.
okay. Dharmik,
Sir, I am still solving, sir.
you need a hint?
No, sir, for now.
Sir,
Prashasti, any issues?
excuse me, sir.
Yeah, Ansh.
Yeah, so when you say that it is how much 1 lakh Newton meter cube per hour and meter cube per hour and
Huh,
meter cube,
huh.
and then you have mentioned 200 degrees Celsius and 20 bars. So what's the relation like? Will the 1 lakh get converted into another number due to the temperature and pressure?
Choice is yours whether you want to use some data or you don't want to use some data. If you think some data is not required for solving the problem, don't use.
Because when we say it is at STP, then
Hmm.
the temperature and pressure are different, but it can change at different temperatures and pressures.
Correct. So what I'm trying to say is if you think that some data is irrelevant for solving the problem, don't use that data.
Yes, sir. Okay.
No harm if I give more data, right?
Yes, sir. Yes, sir.
Prashasti, any issues? You need hints? You're solving? Stuck anywhere? Siddhant, are you solving? Any doubts? Anywhere you're stuck? Just trying to take some names which I've never taken. Swaroop,
Solving, sir.
okay. Are you stuck anywhere? Need hints?
No.
Okay, good, excellent. Good that you don't need hints. Aniruddha,
Sir,
answer.
I need
Yes,
more
sir.
time for sir.
Okay, okay. How much more time?
Can't say now.
Oh, can't say. You need that much time that you can't say also how long it will take. All right. Deepak, do you need more time?
yes, I'm solving it.
Aniruddha, I thought you would have finished long back. Oh, there are two Aniruddhs in class.
Yes, sir, I'm still solving, sir.
Oh, okay. I'll just be back. Okay, any other? Do people need more time? 5 minutes, 10 minutes?
Yes, sir.
Yes, sir.
So dry bases, I've got the volume percent,
Okay, tell me.
91% for N2,
Okay,
8.1% for O2, and 0.9% for CO2.
okay. That is one answer. So if you got that, you would have got the kgs of CO2 per metric ton of terephthalic acid also.
So I'm yet to do that.
Okay, okay. Bhakti, any doubts, any issues, any hints?
No, sir.
All the three Atharvas in the class?
2 minutes, sir.
Okay,
trying.
okay. Trying, are you stuck anywhere, Atharva? Which Atharva am I talking to? Atharva, what is your name, Atharva?
Nangre.
Atharva Nagri, okay.
Hello, sir.
Yeah,
Sir, the selectivity would be same in mole percent and weight percent.
selectivity means amount reacted in the desired reaction. Where did that definition go? Yeah, amount selectivity means amount reacted in the desired reaction divided by amount reacted in the desired reaction plus undesired reaction into 100. So whether I talk in terms of kgs or whether I talk in terms of moles, it would be the same because I'm multiplying or dividing by molecular weight in the denominator as well as numerator. Isn't it?
Yes, sir.
Sir, we will also take the side reaction into consideration, right?
Which side reaction?
Sir,
Acetic acid
the
burning, na?
yes, sir.
Yeah, of course, it is happening whether you like it or not. Obviously, we don't like it, but it is happening all the time. It is just a waste of acetic acid, no? But it is happening. We don't, because temperature is high, pressure is high, catalyst is there, and oxygen is there, and combustible material, acetic acid is there. Hydrocarbon. Who else we have not talked about? Craig, any answer?
Solving, sir.
Sir. Excuse me, sir. Excuse me, sir.
Yeah.
N2 is 90%.
Okay. 90.
Oxygen 90.6, 9.6,
9 points. Oops. 9.6. Okay.
and 0.4 CO2.
Kgs of CO2 per metric ton of terephthalic acid. This answer. How many kgs of CO2 are generated per metric ton of terephthalic acid produced?
Calculating, sir.
Sir, for the acetic acid reactions, or so the side reaction, do the same levels of selectivity and conversion apply to the acetic acid reaction too?
No, is there a desired reaction of acetic acid?
No, sir, but in the acetic acid acts as a catalyst for the first reaction, and also
Acetic acid is a
there's a side reaction.
solvent. Acetic acid is a
Oh.
solvent, not catalyst.
Yes, sir.
So what are you asking, Anirudh?
Sir, so if it acts as a solvent, it will come out fully like a whole, sir, as in it will remain unreacted, sir, for the solvent part. But for the combustion part, what is the split up, sir? As in, how
Split up
much do we
of
take for the
what? Split up of
Oh,
what?
sorry, sir. Sorry, sir. I didn't see the 40 kg of seeds. Sorry, sir.
Yeah, no problem.
So
Yeah,
the tons of CO2 per kg of terephthalic acid formed is 0.05.
tons of CO2 per kg or kgs of CO2 per ton?
So I've taken both in tons.
So are you telling me ton per ton or kg
Yes,
per
sir.
ton?
Ton per ton.
So tell me kg per ton.
Okay, 1 minute.
Ton per ton, if you know, kg per ton is just multiplication by a factor of 1000.
50.
50. All right.
Sir, if we want a better answer, like I've rounded it off, it is 52.6 kg.
Okay, 52.6.
And the percentage of weight percent of terephthalic acid is 27.
Forget that. Forget this. Forget this. Just tell me these two things.
Yeah, so when we calculate a kg of CO2 per metric ton, we will have to consider CO2 from both the reactions, right?
Yes.
From both the combustion reactions.
Correct.
Yes.
CO2 is generated from both, whether you like or you don't like. You don't have a choice. Acetic acid gets burnt because of high temperature, pressure, and oxygen. We don't want it, but it is happening. Corona also we don't want, but it is happening.
I'm getting kg of CO2 generated as 79.33.
79.3. And your composition of the flue gas on dry basis?
I have calculated the moles. I have to convert it to percentage. Just a minute.
Okay. Ria, any answer?
So for the kg of CO2 generated per metric ton of terephthalic acid, I'm getting a 79.11.
Okay, 79.1, very similar to 79.3.
And so this volume thing I'm trying.
Okay.
Yeah, I'm getting the volume percent as 90.2.
Okay, 90
8,
point nitrogen,
8.41,
8.4 oxygen. So
and
balance
1.4.
1.4 is CO2. Okay. I have no idea what the answer is. So maybe
Sir, I'm
one of
getting
you,
80.07 kg.
80.7. 80.7 or 80.07?
80.07.
07.
07.
So we'll just round it off to
Yes.
80.1.
Sir,
Yes.
I got 82.86, the third answer.
Yeah. 82.9, shall we say? 82.86, we'll just round off. Nishant?
Sir, I'm getting 65.3 kg.
65.3. Nishant Amrapali, your volume percent of flue gas, dry
Sir,
basis?
90.88.
90.88. So we'll just say 90.9. Just round off and tell me. No?
7.6.
7.6.
1.4.
1.4. They don't add up to 100.
They do 99.9.
So kg of CO2 generated is 82.7.
And volume percent?
So
of
that
flue
I'm
gas?
calculating.
Okay. Amrapali, your composition of flue gas?
Sir, I'm calculating that.
Who else was giving the
Sir,
answer?
my composition of flue gas matches Arya's.
Which one is that? Now I don't
The
remember
first
which
one, the first one.
Okay.
And my kg of CO2 generated is coming 25.
25. All right. how did you get 25? Something wrong. $25.
Sir, I'm just checking the calculation right now. Just 1 second.
See, no, don't check the calculations. Who was answering that 20? Whose answer was 25? Shaurya Raj. No, whose answer was that?
Yes, sir, mine.
Shaurya Raj. Shaurya Raj, the reason I am telling 25 is likely to be wrong is because of this. See, how much acetic acid is burning per metric ton? 40 kgs, right?
40 kgs, yes, sir.
So if you say that if you make, even if carbon dioxide is coming only from this, even if, okay, carbon dioxide is coming from the other reaction as well, but even if carbon dioxide is coming only from this, then what is the stoichiometry? CH3COOH plus oxygen is giving us CO2. So obviously twice CO2 and H2O. Now I have 4 hydrogens on the left hand side. So I have to have 4 hydrogens on the right hand side. I have 2 oxygens plus 4 oxygens, 6 oxygens minus 2 oxygens. So I need twice of oxygen. So 1 mole of acetic acid burns, I'm going to get 2 moles of carbon dioxide, isn't it? So, or if you like kilomoles, I'm going to get 2 kilomoles. So kilomole, 1 kilomole of acetic acid, molecular weight is 60. That means 60 kg of acetic acid burn, I'm going to get 88 kgs of carbon dioxide. Shaurya Raj, are you with me?
Yes, sir. I'm just revisiting that calculation.
No, don't revisit. Just pay attention. That's what I'm telling you. Don't revisit. Now, if I take 1 metric ton of terephthalic acid, even if all the carbon dioxide only comes from this side reaction, I will have 40 kgs of acetic acid burning.
Yes, sir.
Correct.
So,
So the wait a second, Arya. So amount of carbon dioxide generated would be 40 divided by 60 into 88.
So 58. Yeah, I got it, sir.
No, wait a second. Let me complete. You are super smart and super intelligent, but let me complete what I'm talking because other people may benefit. This will be 58.7. So the minimum amount that would be generated is 58.7 plus the extra carbon dioxide that is getting generated is from here, isn't it? So
yes, sir.
that is the reason I immediately said that 25 seems to be something wrong. Yes,
so
Arya.
I'd like to change my kg of CO2 answer to 81.9%.
What was your earlier answer?
52.6.
Oh, okay. So that you want to change now to
81.9.
81.9. Oops. Not red. Let me draw black. 81.9. Okay. So Shaurya Raj, have you understood why I said 25 looks to be?
Yes, sir.
Yeah. Okay.
Only one of the reactions will give at least 58.
Correct.
And the other will generate easily more than that. I by mistake, sir, I
no
considered the tons instead of the moles for one of
issue.
the reactions.
No issue at all. Only thing I am saying, the lesson out of this is that how we can quickly check our answer.
So
Yes.
I've got kg of CO2 as 79.5.
79.5.
Sir,
yeah,
I'm getting the kgs as 80.44.
80.4. We are just rounding off to 1 decimal place.
Yes, sir.
So the kg part I got 79.3 before, but I would like to change it to 80.1.
Okay. Oops. So you would like to change it to 80.1. So 80.1 is already there.
Yes, 80.1.
Okay. Okay. Do you people need more time, or should we
So
start
more
solving?
time.
Okay.
So
How
more
much
time.
more time? How much more time, Hardik?
So 5 minutes.
5 minutes. All right. All right. So one problem is taking now more than 1 hour.
Sure, please could you show us the please can you show the quantities which are to be found?
Here. Kgs of CO2 generated per ton of terephthalic acid produced and composition of flue gas on dry basis in volume percent. Even if you tell me these two things, other things are will be in accordance with this. If these are correct, all the other things will also be correct.
Sir,
Yeah.
for the volume percentage, sir, I'm getting nitrogen as 89.96. You can round it out. Yes, sir. 89.96, 8.63, and 1.41. Yes, sir.
excuse me, sir.
Yeah.
I got 81.9 as the kgs of carbon dioxide produced. My answer matches now. I corrected it, and my composition has come to 89.25 of N2, 9.3 of O2, and 1.4 of CO2.
Hardik, can we see the solution?
Yes, sir.
I was waiting for you only.
So I've got the third answer. The kg of CO2 generated as 65.7.
Okay. Okay, so let us start solving. So how we are going to solve? We are going to look at all the quantities, compositions in the reactor, coming in, going out of the reactor. We are going to write everything by means of tables. So we have paraxylene coming in, we have acetic acid coming in terms of kgs per hour. If you want to write, this would be 20,000 kgs per hour, and this would be 80,000 kgs per hour, right? That's what we have, 80 tons and 20 tons, right? Okay, so because we are going to talk about reactions, we also need to convert this into kilomoles per hour. Okay, so we are not going to see the solution per se, we are only going to see how we are going to solve. Okay, so this you can calculate. Right, this can be calculated. Okay, next thing that we know is, we know 100,000 n m cube per hour, and remember that n means that it is meter cube at STP per hour, and this is going to contain now nitrogen and oxygen in terms of mole percent or volume percent. They are same. This is 79 mole percent and 21 mole percent. Now this 100,000 you can convert to kilomoles per hour. Will you be able to do that? Use the ideal gas law. So what are we saying? If we are saying STP conditions, that means 1 atmosphere absolute pressure and 0 degrees centigrade. 0 degrees centigrade means 273 Kelvin. 1 atmosphere absolute means 1.013 into 10 raised to 5 pascals. Okay, so if you want number of moles, that is PV by RT. So pressure is 1 atmosphere, so 1.013 into 10 raised to 5. V is 100,000 meter cube per hour. Remember, Pascal is Newton per meter square. R we can take as 8.314 joules per gram mole Kelvin, but then our answer will be really, really huge. So I can even take 8314 joules per kilomole Kelvin, and temperature would be, we can say 273.15 if you want. 273.15 Kelvin. So Kelvin would get cancelled. Joules will get cancelled from this Newton per meter square and per meter cube. So this will come in terms of so many kilomoles per hour. Do you agree with this? Anybody has doubts up to here? So we'll be able to get this kilomoles per hour, right? And because we are talking in terms of reactions, we need to convert this also in terms of kilomoles per hour. So once we know the total kilomoles per hour and the mole percent, we can calculate these two quantities as well, right? We are not going to solve, we are just going to see how to solve. So you can solve at your own pace. The methodology is there. Anyway, the recording is going to be shared. So if you're stuck somewhere, you can always check back. The flue gas now, in terms of nitrogen, oxygen, and CO2, and water. We can say kilomoles per hour. and we can say mole percent or volume percent. They are the same. Okay, but remember we want it on dry basis, so we will leave out the water for calculating the percentages. Okay, now what comes out of the reactor, the liquid stream is going to contain terephthalic acid, is going to contain paraxylene, it is going to contain the acetic acid. Because we are talking about reactions, we will do in terms of kilomoles per hour. Okay, and then if required we can do kg per hour and weight percent and all those things we can do. Okay, any doubts so far?
Sir, paraxylene will not be present in the liquid stream out.
Okay, why do you say that?
Sir, it will be reacted completely.
Who says it will be reacted completely?
Sir, Ohm.
Didn't we say that conversion of paraxylene in the reactor is 98%? What does that mean? 98% of whatever is fed reacts, right?
Sir, so means it 98% reacts in desired reaction and
Conversion. What are we talking about? Conversion. How did we define conversion? That's why I spent some amount of time in the start of the lecture. Amount reacted in the desired plus undesired, both reactions. You see that?
Yes, sir.
Okay, divided by amount supplied. That's why I spent some amount of time in the start of the lecture. All right, let's continue solving. Now, what are our reactions? Our reaction is paraxylene plus oxygen, desired reaction, giving us terephthalic acid and water. So can we say 1 mole of paraxylene reacts with 1 mole of oxygen, giving us 1 mole of terephthalic acid and generating 1 mole of water? Can we make that statement?
No, sir.
No. So we need to balance the reaction. So tell me the balanced reaction. Somebody tell me the first reaction, balanced reaction. Paraxylene plus how many oxygens?
Three oxygen.
Three oxygens, giving us 1 terephthalic acid. How many waters?
Two
water. Okay. Second reaction, somebody can balance. Paraxylene plus oxygen giving us carbon dioxide and water.
Oxygen is 21 by 2.
21 by 2.
10.5.
Yes, sir. 10.5.
10.5. Okay, let me write it as 10.5. Okay.
8
Carbon
CO2. 8 CO2.
8 CO2.
8 and 5. 5 H2.
5
5 H2.
All right. What about this? Acetic acid plus oxygen. This we have already balanced, right? So acetic acid plus 2 oxygen give us 2 carbon dioxide and 2 water. Okay. Now let's just calculate some small things so that we know 20,000 kgs per hour of paraxylene is how many kilomoles per hour of paraxylene? Molecular weight of paraxylene is how much?
188.7 kilomoles.
Molecular weight of paraxylene is how much?
106.
106, right? So this is 188.67. So let's just say 67. Okay. Now, if we have to calculate how much paraxylene will remain unreacted coming out of the reactor, how will we calculate that? We know that 98%. Correct. 98% of this 188.67 is reacting. That means what remains is 0.02 multiplied by 188.67. Okay. Now, how much paraxylene is reacting? It is 98% of 188.67. How much paraxylene is reacting in the desired reaction? It is 0.98 multiplied by 188.67. Selectivity
0.99.
99%. Selectivity means amount reacted in the desired reaction divided by the total amount reacting. Selectivity is 99%. So paraxylene reacting in the desired reaction is 0.98 into 188.67 into 0.99. Paraxylene reacting in undesired reaction is 0.98 into 188.67 into 1%, 0.01. Let's just calculate these numbers. 0.98 into 188.67 into 0.99. This number is 183.05 kilomoles per hour. Write the units. The second number is 0.98 into 188.67 into 0.01. This is 1.85 kilomoles per hour. Okay. Now, how much terephthalic acid will be produced? 1 mole of paraxylene reacts will give me 1 mole of terephthalic acid. Our reaction is balanced now. So that means amount of terephthalic acid produced would be 183.05 kilomoles per hour. If we write that in terms of kg per hour, how much will be kg per hour? Multiply by molecular weight. 183.05. What is the molecular weight of terephthalic acid?
166.
166. So this will be 30386.3 kgs per hour. So how many metric tons per hour of terephthalic acid is produced?
30.38.
30.3863. So we can just say 30.39, just round it off. Okay. So how many
Sir.
kg? Yeah.
Sir, the paraxylene is also reacting with oxygen, so means it will be a chemical reaction, so it will depend on limiting reagent and that all, no? So how we can directly say that 183.05 is reacting, means is coming out?
But didn't we say that there is 98% conversion in the reactor?
Yes, sir. So
98% conversion means out of 188.67 that is reacting, how much has reacted? Total paraxylene reacted is equal to 0.98 multiplied by 188.67 kilomoles per hour. Selectivity is 99% means 0.98 into 188.67, that is the total reacted, into 0.99, 99% is 183.05. So if 183.05 moles of paraxylene react, how many moles of terephthalic acid will be produced? What is the stoichiometry? One paraxylene is going to give me 1 terephthalic acid, isn't it?
Yes, sir, but oxygen is also there, no? So it will not create anything.
Anyway, we have balanced this reaction. No? Oxygen, we have not yet written for how much oxygen reacts. That we are still writing. We are still not completed the problem, right? Now, what is your doubt? I am unable to understand what you are asking.
I think he means to say that what if the oxygen gets finished before all of the paraxylene is reacted?
What if all the oxygen gets consumed before all of that? Oh, we will talk about that. We will talk about that, isn't it?
Okay.
But I never said it is conversion of limiting reactant. All I have said is conversion of paraxylene.
Okay, sir.
Isn't it? I mean, if I had written conversion of limiting reactant, then your doubt would have been okay. but I'm telling you that it is conversion of paraxylene in the reactor. But your doubt is still valid, that what if that 98%, if all the oxygen gets consumed even before it makes 98%, even if it before reacts 98%, right? Your doubt is still valid, but we will answer that. We'll talk about that. Okay, so so far okay.
Yes, sir.
Okay, so now metric tons per hour of terephthalic acid produced is 30.39. So kg per hour of acetic acid burning is 40 into 30.39 kg per hour. In terms of kilomoles per hour of acetic acid burning, it will be 40 into 30.39 divided by molecular weight of acetic acid 60. So 40 into 30.39 divided by 40 multiplied by 30.39 divided by 60. Somebody calculate this number. It is 20.26 kilomoles per hour. Okay. Now can we start doing oxygen balance? Or we can start doing terephthalic acid balance. Okay, 80,000 kgs of 80,000 kgs of acetic acid per hour come in. So 80,000 divided by molecular weight 60, it is 1333.33 kilomoles per hour of acetic acid come in. How much acetic acid is burning? 20.26 kilomoles per hour of acetic acid is burning. So acetic acid going out would be 1333.33 minus 20 point, how much was that number? 20.26. Okay. And then we can convert this also into kg per hour. Now, whoever was asking about oxygen, let us start worrying about oxygen. Okay, how many total kilomoles per hour come in? We have seen this. So 1.013 into 10 raised to 5 into 100,000 divided by 8314 divided by 273.15, or you can simply use 1 liter at STP corresponds to 22.4 gram moles, or 1 meter cube at STP corresponds to 22.4 kilomoles. That also you can use, or you can use the ideal gas law. They are the same. So this would be 4461.75 kilomoles per hour. Now, how much nitrogen would there be? 0.79 multiplied by 4461.75. How much oxygen will there be? 0.21 times 4461.75. Somebody tell me these numbers. 0.79 into 4461.75. Somebody
3524.8.
Okay, 3524.8 and 0.21 multiplied by 4461.75.
936.97.
936.97. Okay. Now, can we start doing oxygen balance over this control volume? This is our control volume. Okay. Now, oxygen is reacting with what? Oxygen is reacting with paraxylene to give you the terephthalic acid. This is one place where oxygen is reacting. Another place oxygen is reacting is the second reaction, undesired reaction. And the third place as oxygen is reacting is this acetic acid burning reaction. Okay, so now oxygen going out of the reactor, oxygen going out of the reactor if you want to write, what will we write? Before that, nitrogen is unreacted, so straight away 3524.8 kilomoles per hour will go out. Oxygen that will go out would be 936.97 minus oxygen reacting in the first reaction. How much oxygen is reacting in the first reaction? It is the paraxylene reacting in the first reaction, 183.05, isn't it? Plus paraxylene in the second reaction. Now, when 183.05 kilomoles per hour of paraxylene react in the first reaction, how much oxygen would react? It would be 183.05 multiplied by how much?
3 times.
183.05 multiplied by 3. Why is that 3? That is the stoichiometry. Stoichiometry. In the second case, second reaction 10.5. Right? So what is the paraxylene reacting in the second reaction? Where did that go? Paraxylene in this reacting in the second reaction was 1.85. So oxygen going out would be 936.97 minus 183.05 into 3. That is what is reacting in the first reaction, minus 1.85 multiplied by 10.5. Minus, now oxygen is also reacting with acetic acid. How much acetic acid is burning? 20.26 kilomoles of acetic acid are burning. One molecule, 1 mole of acetic acid reacts with 2 moles of oxygen, isn't it? So amount of oxygen reacting with acetic acid is 20.26 multiplied by 2. So this is minus 20.26 multiplied by 2. Do you agree with that? Anybody agrees with this? Anybody disagrees with this?
Yes, sir.
Anybody has any doubts? So now we can calculate the carbon dioxide as well. Okay, same way we can calculate carbon dioxide. Whatever is generated from first reaction, whatever is generated from second reaction, whatever is generated from the third reaction. Fortunately, in the first reaction, no carbon dioxide is getting generated. Carbon dioxide is getting generated only from second reaction and third reaction. So carbon dioxide generated from second undesired burning plus third reaction, acetic acid, right? Now we can find out all these compositions. Kilomoles per hour we have, now mole percent we can find out, water also we can find out. Okay, so let's just do this. Carbon dioxide generated from second reaction and carbon dioxide generated from third reaction. Second reaction, how much paraxylene is reacting? 1.85. 1.85 kilomoles of paraxylene is getting generated. 1.85 kilomoles per hour of paraxylene is reacting in the undesired reaction. What is the stoichiometry? 1
times.
Paraxylene will give us 8 moles of carbon dioxide. So this 1.85 multiplied by 8 plus second, the side reaction of acetic acid, 20.26 into 2. 1 mole of acetic acid reacts, it gives us 2 moles of carbon dioxide. So how much is this number total? 1.85 into 8 plus 20.26 into 2. This is 55.32 kilomoles per hour of acetic acid. If it is 55.32 kilomoles per hour of acetic acid, 55.32 kilomoles of carbon dioxide. What is the molecular weight of carbon dioxide?
44.
40?
44.
44. So if I want to write in terms of kg per hour, 55.32 multiplied by 44, that would be 2434.08 or 0.1 if you want. Okay. So how many kgs of carbon dioxide are generated per ton of terephthalic acid produced? How much is that? 2434.1. This is 2434.1 divided by tons. How many tons of terephthalic acid are produced? 30.39. Okay. Divided by 30.39. This is 80.1. Okay. Now, anybody has any doubts? Will you be able to solve?
So I have one doubt.
Yes.
That is, if we whoever has solved via this method, and we are having a very small difference, and if we take the average of all of those answers, will we go to the right answer?
No. Average of which answers? Average of all of these answers?
Not all of these, but whoever has solved via this method, and we are having.
Via this method means there is no wrong method, right method. Whatever method you want to adopt, you can adopt.
Yes, sir. But I think what is the error? I mean, margin of error, sir. As in, how can we round it off, sir? Like, in some places,
Margin of
we've
error.
rounded it
Margin
off.
of error means if you are saying that if my answer is 80.1 and your answer is 80.07, you mean to say that I mean to say that you will not get 0. I mean, why do you worry about margin
Yes, this
of
is understandable.
Why do you worry about this margin of error? I mean, it is not some computer.
No, sir,
it is not some
basically-
computer. Wait, let me complete. It is not some computer checking your answer, right? That JE you will get, if you have marked it as D, you will get 0. If the answer is C, you will get some 2 marks or 5 marks or whatever. Why do you worry about these things, Baba? What is the margin
yes, sir,
of error?
understood,
What is the
sir.
margin of error? What is the accuracy of your CO2 measurement? Do you know how CO2 is measured? CO2 is measured using an IR, infrared detector. Right? So what is the accuracy of that detector? That is what is going to tell you what is the level of acceptable accuracy here. Whether it is 80.1 kg per metric ton, or whether I say 80 also, it is okay. Isn't it? There's no point in calculating an answer which is 80.111345. Your detection has no accuracy up to so many decimal places. Again, what I'm saying is if your answer is 80.1345, and let's say, suppose somebody rounds it off to 80.1, how much error is made? It is 0.0345 divided by 80.1345 or 80.1, even if you want to say, into 100. 0.0345 divided by 80.1 into 100. So your answer is accurate up to 0.043%. Is your detector capable of having accuracy more than this? That is the question. If it is, then it is worth having second decimal place. Otherwise, it is not worth having second decimal place because nobody can verify. Isn't it? Do you agree? Anirudh, do you understand?
Yes, understood.
So don't bother about whether you round it off, whether you don't round it off, whether you take average of all of these. Whether you want to take average of all of these and get the answer. I don't know whether all these right answers are right or wrong. Whether there are any, is it only because of round off errors, or is it because some error has been made in calculations? Obviously 65, there seems to be some error, right? Maybe 81.9, 79.1, maybe 79.1 also seems to be some error. I don't know.
Yes, sir, that was my doubt, sir. In between some rounding off, like sometimes
Rounding
we
off-
might make a mistake. So
rounding off will not give
around
you
that, like
65.3.
around the answer, which is 82.1.
No, rounding off will not give you 65.3.
Yes, sir.
Whoever has got 65.3,
Yes, sir.
check for yourself whether it is based on round off errors or there is some error in the calculation.
No, sir, there is a conceptual error.
Okay, fine. You don't have to answer to me. You have to just answer for yourself. See for yourself. Okay. So is there a, so can we go forward now? Everything
Yes, sir,
we have
yes,
been
sir.
able to get?
Thank you.
Yeah, no problem. Shall we go to the next problem? A very small problem, but just to help you practice, right? And then we'll take a detailed problem based on this. So there is a reactor that makes ethylene oxide. See, so a couple of points I want to mention. I will give this problem, then I will mention this this issue. So let's say this ethylene oxide reactor, ethylene oxide is made from ethylene and oxygen. So ethylene plus oxygen gives you ethylene oxide. Okay, so this is a high temperature reaction. So what I do is we feed ethylene gas along with oxygen. So this is a gas, plus there is some inert. So inert is, let's say, methane is an inert material right now in terms of volume percent. So ethylene is 25 volume percent, oxygen is 5 volume percent, and balance 70 volume percent is methane. Okay. Now, because it's a high temperature reaction, some ethylene also gets combusted to carbon dioxide and water. So obviously, if we are making ethylene oxide, this is our desired reaction and this is our undesired reaction. Okay, methane we are saying does not burn at all, does not react at all. Okay, let me describe the problem. Okay, so what I'm going to tell you is percent conversion of ethylene is how much? Let's say 10%. Okay, very small amount of conversion we keep so that we limit the undesired reaction, and percent selectivity to ethylene oxide is 85%. Okay, let me.
So
tell you
the
once again.
undesired reaction gives H2O or H2?
Sorry, not obviously burning. It is not H2. It is water. It's burning, right? Burning will not give you hydrogen. Burning will give you carbon dioxide. So this gas stream that comes out, conversion means out of the total ethylene that I feed, 10% reacts, balance 90% remains unreacted. So obviously reactor gas coming out, I will have unreacted ethylene. Methane is going to remain unreacted. I have told you. Oxygen, some amount of oxygen may remain. I don't know. Plus ethylene oxide will be there. So let's just call it as EO. So this is our EO, ethylene oxide. All of this is a gas. It's a total gas phase reaction. Gas, 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 gas. High temperature. Gas. Okay. Some amount of carbon dioxide will be generated. Some amount of water will be generated. Okay. Is that okay? So conversion of ethylene is 10%. That means if I feed 100 kilomoles of ethylene, 90 kilomoles of ethylene will remain unreacted. 10 kilomoles of ethylene will react. selectivity to ethylene oxide is 85%. That means if 10 kilomoles of ethylene are reacting, 8.5 kilomoles of ethylene will react in the desired reaction. 1.5 kilomoles will react in the undesired reaction. Selectivity. Okay. I want to make 200 metric tons per day of ethylene oxide. Okay. Can you calculate quantities and compositions of inlet and outlet stream? Okay. Inlet stream, obviously composition I have given you. I only want quantities. So quantities you can tell me in terms of kilomoles per hour. Okay. And composition obviously in terms of volume percent or mole percent. Okay. And if you want, composition can be on dry basis. Because water is there, we are going to talk about it on the composition on dry basis. Okay, that is one thing I want you to calculate. Second thing I want you to calculate is kgs of CO2 produced per metric ton of ethylene oxide produced. Right, all the carbon dioxide is coming from this side reaction. Right, we are saying methane remains unreacted. Temperature is high, but it is not so high that methane will also react. And then there is a catalyst. If you know a little bit about ethylene oxide manufacturing, this is a silver is a catalyst. And on that catalyst, methane does not react, but ethylene reacts. And therefore, we are assuming that methane remains unreacted. Only these two reactions are happening, desired and undesired. Okay, will you be able to solve?
Yes, sir.
So try solving.
Yes, sir.
If you are stuck, let us, you can discuss amongst yourselves. I don't have the answers, so there's no point in asking me. Better you ask your classmates if they have an answer. Now, what we are going to do, the point that I wanted to make, all right, why we are worried about things like this? Why we are worried? Why do you think we are worried about how much kgs of CO2 are produced?
For environmental
pollution, sir.
pollution control.
It is a CO2 is a greenhouse gas, and nowadays everybody is talking about how much CO2. So if you are, so this is the second problem if you want. Second problem. Now suppose you buy a shirt. Let's say weight of that shirt is 1 kg. Okay, obviously shirt will not weigh 1 kg, but or buy shirts 1 kg. And let's assume that the shirt contains only pure polyester. Okay, obviously shirt will have color, dye, thread, all those things, but let's assume that it is only polyester. Now what is polyester? It is terephthalic acid. Oops, sorry. Terephthalic acid. Sorry. Terephthalic acid and ethylene glycol. It's a condensation polymer of these two. Okay, so if you want to write it like this, COO C2H4OH and C double bond OH. That is if one reacts, one molecule of this and one molecule of this react. But obviously this end group, there is an acid group at the end. There is also a OH group at the end. So we can say that if N molecules react, we can say that I will have C double bond O, another O C2H4, isn't it? But that another C2H4 will have another OH at the end. So it will keep on reacting. So polyester, we are going to write in a general form like this. N. Okay, and then N and N will react, isn't it? Forget, the chain will be so big that you can forget about the last molecule of terephthalic acid and last molecule of ethylene glycol. This is your generalized formula for polyester. All right, everybody okay with this? Yes, no?
Yes, sir.
Yes, sir.
Now, where are we going to get this ethylene glycol from? Ethylene glycol is going to come from hydrolysis of ethylene oxide. So ethylene oxide, if we hydrolyze that, we will get ethylene glycol. This is your ethylene glycol. EG if you want. This is ethylene oxide, EO. Okay. So if you take 1 kg of polyester, it is going to require so many kgs of terephthalic acid, and it is going to require so many kgs of ethylene glycol. Even if you say complete conversion, 100% conversion, right? Stoichiometric reaction. 1 kg, so many kgs of terephthalic acid are going to correspond to so many kgs of CO2. This is only considering the CO2 from reactions, 80.1, right? 80.1 kg of CO2 per metric ton of terephthalic acid, per metric ton. So many kgs of ethylene glycol from this second problem that you solve, this problem that you are going to solve, you will get so many kgs of carbon dioxide generated per metric ton of ethylene oxide. And then you can convert that to kgs of CO2 per metric ton of ethylene glycol. So when you buy 1 kg of polyester, this is the net environmental impact that you are going to cause. Do you realize? So that is something, that number, total kgs of CO2 generated per metric ton of something. In this particular case is the polyester. This is called as carbon footprint. So if you just do Google carbon footprint, you will get this number. Okay. By the way, we are considering only the amount of CO2 that is generated by way of reactions. Plus, so many other places we are using energy. We still have to worry about how much CO2 is generated. What is the CO2 footprint of electrical energy? We will do all these as we go along. Okay. So in terms of our sustainability, we need to worry about what is our carbon footprint. 1 kg polyester, if we use or if you buy, that much amount of carbon dioxide you are generating in the environment. So be conscious about what we are doing to the environment. Don't be conscious about whether it is 80.1 or 80.05. Okay? Be conscious about this. is your living sustainable? That is why we are doing this course, not because of giving you grades. All right, that is why this course is there in the syllabus. You can calculate all these things to make things more sustainable, to make products more sustainable. Right? Shall we stop for the day? Anybody has any doubts? Quick doubts we can have. Yes.
Sir,
No?
it should not be 80.1, no?
Why?
It should be the multiplication of kg.
Yeah, obviously.
So it is not the final.
No, I am only saying it is 80.1 kgs of CO2 per metric ton of carbon, per metric ton of terephthalic acid. I will have to multiply by this, obviously. Then I will give you total kg per metric ton of whatever product. If I'm talking about terephthalic acid, it is 80.1. If I'm talking about polyester, it will be something different. That's what I want you to calculate. I have shown an arrow. I have not said equal to. I have said you can calculate. Is that okay?
Yes, sir.
Okay, so shall we stop for the day?
Okay.
So one point I would like to mention is you seem to be having some lecture in the afternoon, isn't it? Some lecture is there in the afternoon, right? Harsh? Yes. Arya?
Yes, sir.
So if your lecture is not there, shall we meet at 3 o'clock?
Okay.
There seems to be good possibility that afternoon lecture is there, because already in the message, Arya, you are saying maybe at so and so time. So if your lecture is not there, can you send me a message? Then we can meet at 3 o'clock.
Okay, sir.
All right. We can use the same link. We don't have to look for another link.
Sure, sir.
If your lecture is not there, if your lecture is there, obviously that lecture is a priority.